In the previous lecture of this part 6 of Applied Linear Structures, we talked about linear transformation, and based on that concept, we defined eigenvalues and eigenvectors. We realized how to calculate eigenvalues for a given matrix, and then based on those eigenvalues, we could find the corresponding eigenvectors. We also saw how we can find eigenvalues and eigenvectors both using Python and MATLAB. In this lecture, we are going to dive into decompositions. So in this lecture and the next few lectures, we are going to talk about LU decomposition, QR decomposition, eigendecomposition, and singular value decomposition. All right, let's start with LU decomposition. The goal of this lecture is to see the definition of LU decomposition and understand how LU decomposition breaks a matrix into a multiplication of two matrices, that one of them is lower triangular and one of them is upper triangular. And then I'm going to talk about how we can find the L and U component of a matrix using LU decomposition in Python and MATLAB. After that, I will share some insights about why LU decomposition is useful in computing, specifically when we want to solve a given linear equation like A multiplied by X is equal to B, where A is a matrix of multipliers, X is a vector of unknown variables, and B is a given vector of unknown values. And at the end of the LU decomposition, I'm going to show one example where LU decomposition can help us to solve a linear equation. All right, the LU or lower upper decomposition or factorization decomposes a matrix into product of an upper and lower matrix. So A is equal to LU, where L is an upper triangular matrix. What does upper triangular mean? It means all of the elements below the diagonal are 0. So we put a big 0 here, and then we have U sub 1, 1, U sub 2, 2, U sub 3, 3, and so on. U sub 1, 2, U sub 1, 3, and so on, U 2 sub 3, and so on. All right. As well as a lower triangular matrix with all of the diagonal elements equal to 1. So this is the representation of LU decomposition for a 2 by 2 matrix. We have L matrix or lower triangular matrix, and we have U matrix or the upper triangular matrix. This decomposition is very useful in solving Gaussian elimination problem, and also plays a key role in both inverting a matrix, computing determinant of a matrix, and as I mentioned, solving a linear equation or a set of linear equations such as A multiplied by X is equal to B. The good point is that you can solve a system of equations systematically when you have the LU decomposition of matrix A. All right. So let's see, for example, what's the LU decomposition for matrix A, which is defined as 4, 3, 6, 3. So A is equal to LU. As we mentioned, L is a lower triangular matrix with all of the diagonals equal to 1, and the lower diagonal are values, so we don't know the values. And U is an upper diagonal matrix. What does that mean? Whatever below the diagonal is 0, U sub 1, 1, U sub 1, 2, and U sub 2, 2. So if we multiply these two, as we said, this row multiplied by this column, U sub 1, 1, this row again multiplied by the second column, U sub 1, 2. This row, L2, 1, 1 multiplied by the first column, L sub 2, 1, U sub 1, 1. 1 and 0 cancel each other. And then this row and the second column, which is L sub 2, 1, U sub 1, 2 plus 1 multiplied by U sub 2, 2. All right. Given all this, we can make the equivalence for element by element. So let me use another color. So 3 is equal to U sub 1, 2. 6 is equal to L sub 2, 1, U sub 1, 1. And last but not the least, 3 is equal to this. All right. So this is what we did here. We use the same color, so we can correlate the colors with this. All right. And we have 3 is equal to U sub 1, 2. And finally, we have U sub 1, 1 equal to 4. So solving the variables in that equation above gives us the LU decomposition for matrix A. So matrix A, we decompose it into L and U, lower and upper triangular matrices. So this was just an example of 2 by 2 matrix, but it can be generalized to n by n dimension. But again, as I mentioned, in this course, we are focusing on applied linear structure for computing purposes. So our goal is to use computer programming, to use scripts from Python, MATLAB, or other programming languages to find these values. So the question is how to find LU decomposition in Python. Using this script, P, L, U is equal to SciPy, or you can also use NumPy. It depends which one you want to use for your code. Dot linear algebra dot LU A. A is our given matrix, which is a square matrix. So you already define matrix X, matrix A. It is available in Python NumPy or SciPy library and can be used to find the LU decomposition of matrix A, i.e. L is a lower triangular matrix and U is an upper triangular matrix. In MATLAB, that's even more simple. We have L, U. This is equal to LU of matrix A. So this gives us L, a lower triangular matrix, and U, an upper triangular matrix. That determines the LU decomposition for matrix A. So now that we have an idea about LU decomposition, I want to provide more insights about using LU decomposition for the purpose of solving a set of linear equations. All right, I try to write it using steps. So step 1, we have AX is equal to B. We use the alternative version of A, matrix A, which is LU, which is this LU decomposition. If we replace A with LU, we are going to have L multiplied by U multiplied by X is equal to B. In the next step, step 2, we define vector Y, which is an n by 1 vector. And how do we define Y? Actually, we use UX. Y is equal to UX, or it's better to show it in the form of linear equations. UX is equal to 1. Let me call this equation 1. All right. And then in step 3, we are going to use UX is equal to Y And we already know that LU multiplied by X is B from here. So what does that mean? We can replace this by Y. So we have L multiplied by vector Y is equal to B. So let me call this equation 2. In the next step, step 4, what I'm going to do, first, I'm going to solve equation 1. Solve equation 1. Ux is equal to Y. What does it give us? It gives us, oh, sorry. First, we solve equation 2. Solve equation 2. Equation 2, which is L multiplied by Y is equal to B. So after solving this, we know value of B, we know value of L. It gives us Y. Now that we have the value of Y, solve equation 1. So we have U multiplied by X is equal to Y. And this gives us the value for X. So step 1, solving equation 2, and then solving equation 1. So this value of Y is going to be replaced here. So this is known, and this is our unknown. So you may ask, why do we need to do this? So what's the motivation for using LU decomposition for solving this linear equation instead of simply solving A multiplied by X is equal to B? The answer is the sparsity. Having a lot of zero values in L and U, it helps us to do computing in a more efficient fashion. So when we have matrices which their dimension is, let's say, 10,000 by 10,000, then having half of the matrix, each of these matrices have 0 elements is going to be very helpful. Also, we can do forward and back substitutions to find Y and X in a more systematic way, which again helps us to formulate and program the problem in a more systematic way when we are using computer program. So now that we know this, let's take a look at example of solving linear equations. So solving linear equations using LU decomposition. Let's say we are given matrix A, which is 2, 6, 2, minus 3, minus 8, 0, 4, 9, 2. And what we want to do, we want to use LU decomposition. Our goal is to use LU decomposition to solve linear equation AX is equal to 2, 2, 3. What is X? X sub 1, X sub 2, X sub 3. What is A? A given matrix. So the very first step is to find LU decomposition. So A is equal to 2, 0, 0, 0, 7, 1, minus 3, 4, minus 3. And U is 1, 3, 1, 0, 1, 3, 0, 0, 1. So as I mentioned before, usually we prefer L to have these diagonal elements all equal to 1. But in this case, we have it for U. How can we switch this? We simply can multiply the first row of L by 1 divided by 2. And then at the other side, we can multiply this by 2 at the same time. So this one is going to change the first row of L to 1. And the first row of U is going to multiply by 2. So this is not going to make a big difference. So at this point, we stick to this. And how do we find LU decomposition? As I said, we can use Python or MATLAB scripts to find LU decomposition here. Then we want to use this result to solve our linear equation. So as I said, x sub 1, x sub 2, x sub 3 is equal to b. In the first step, we define y. So what is y? This part is equal to y sub 1, y sub 2, y sub 3. U multiplied by x is equal to y. And at the first step, we are going to consider L and y and b. This is the value for b. So we are going to have Ly is equal to b, or 2, 0, 0, minus 3, 1, 0, 4, minus 3, 7, multiplied by y sub 1, y sub 2, y sub 3 is equal to b, which is 2, 2, 3. All right. So at this step, what we are going to do, we are going to do something called forward substitution. Why do we call it forward substitution? Because first we solve for the first row. 2 multiplied by y sub 1 is equal to 2. So y sub 1 is equal to 1. Now we use this value and go to the second row. The second row tells us minus 3 y sub 1 plus y sub 2 is equal to 2. And now you already know value of y sub 1. So minus 3 plus y sub 2 is 2. So y sub 2 is equal to 5. And again, it's forward substitution. Let's consider the third row and this column. So we have 4 y sub 1 minus 3 y sub 2 plus 7 y sub 3 is equal to 3. And we already have the values for both y sub 1 and y sub 2. So y sub 3 in this case is going to be equal to 2. So we have y sub 1, y sub 2, y sub 3, y is equal to 1, 5, 2. Okay, keep this in mind, and we know that ux is equal to y. Now we go to the next step of the step-by-step algorithm that we talked about for using LU decomposition to solve a linear system of linear equations. All right, let's see the next step. The next step is we have y is 1, 5, 2. We have x, which is x sub 1, x sub 2, x sub 3. And we have u, which in our case was 1, 3, 1, 0, 1, 3, 0, 0, 1. So we know that u multiplied by x is y, which means 1, 3, 1, 0, 1, 3, 0, 0, 1 multiplied by x sub 1, x sub 2, x sub 3 is equal to 1, 5, 2. Now we need to solve this using back substitution. What does that mean? Let me write each of these in the expanded form. So this row, this row, this row multiplied by this column. X sub 1 plus 3x sub 2 plus x sub 3 is 1. X sub 2 plus 3x sub 3 is equal to 5. So I simply multiply this row by this column and it's equal to this. And finally, this row, this column equal to 2. So the last one is just x sub 3 equal to 2. Now we use back substitution. In the previous step, we used forward substitution. This is backward substitution. And it yields to, we start with the last one, x sub 3 is 2. And we know that x sub 2 plus 3x sub 3 is 5. So we simply replace x sub 3. We have x sub 2 plus 3 by 2 is 5. Then x sub 2 is minus 1. And now So these two are used. We use the first equation, x sub 1 plus 3x sub 2 plus x sub 3 is equal to 1. We know x sub 3 is 2, x sub 2 is minus 1, so we have x sub 1 minus 3 plus 2 is 1. So x sub 1 is equal to 2. All right, the equation is solved. Now we know that x is x sub 1, x sub 2, x sub 3. This is the answer to our set of linear equations. All right, in this lecture, we talked about LU decomposition. The purpose of LU decomposition was having the input A, which is an n by n matrix, and decompose it into two components, a lower triangular component and an upper triangular component. So for the lower triangular component, this is a matrix. These are the diagonal elements, the lower elements, and here we have all zeros. For U, the upper triangular, we have these elements. There are some non-zero elements here, and this is 0. How do we use this? One of the applications is for solving a given linear equation, ax is equal to b. So we said we replace a with lux is equal to b. We consider y is equal to ux. Then we have ly is equal to b, where y is also unknown. Next step, we find y. After we have y is equal to ux. U is known, y is known, and we find the value for x. As we said in the first step, we use forward substitution. In the second step, we use backward substitution. We also saw how we can find L and U decomposition components of matrix A using Python and MATLAB. So that was all for LU decomposition. In the next lecture, we are going to talk about another interesting decomposition referred to as QR decomposition.